You drop a feather, you drop a hammer. Aristotle says one falls faster. 2,000 years, nobody checks. Then a mathematician in Pisa stands on a tower and shatters everything. But here is what almost nobody tells you. The tower story might be a myth. The real genius was not what Galileo dropped. It was what he refused to accept. Wooden ramps, water clocks, bronze balls rolling down grooves. A thought experiment so simple a child could follow it. So devastating it ripped apart centuries of certainty. Galileo did not just prove objects fall at the same rate. He proved something deeper, something that would haunt physics for 300 years until Einstein called it the happiest thought of his life. The way Galileo understood falling bodies was not just genius, it was the birth of how we think about reality itself. If you value documented physics and motion history like this, subscribe. It's the best way to support our work. Also comment from which city you are hearing this from. Also, this script is researched and factual, using sources from Galileo's own published work. 2 New Sciences, published 1638 in Leiden, and scholarly analysis from Physics in Perspective, journal published May 30th in 2017, examining Galileo's early. Manuscripts de motu from around 1590, showing the evolution of his thinking across nearly 5 decades. Now back to the information. A 100-pound iron ball falls 100 times faster than a 1-pound ball. Aristotle declared it. Universities taught it. Nobody questioned it. Because Aristotle was not just a philosopher, he was the standard. The cage around thought itself. He wrote it in Physics and on the Heavens around 350 BC. He said if you drop 2 stones, one 10 times heavier than the other, from the same height, the heavier one would hit the ground, while the lighter one had barely fallen a tenth of the distance. Specific numbers, confident, wrong. His mistake was not observation. It was assuming all falling followed the same pattern. He thought objects quickly reached a steady speed determined by their weight, and then maintained that speed. Constant velocity. No continuous acceleration. This seemed reasonable because when you watch light objects fall through air or water, they do exactly that. They reach a terminal speed fast and then coast. Aristotle took a specific case and made it universal. That is where the crack formed. Young Galileo does not start by rejecting Aristotle completely. He starts by modifying him. He argues that objects of the same material, the same specific gravity, fall at the same speed regardless of their size or weight. 2 lead balls, one large, one small, hit the ground together. Absolute weight does not matter for objects of the same substance. Only specific gravity does. This is not the full truth yet, but it is a crack in the wall. Take 2 stones, one heavy, one light. Assume Aristotle is right. The heavy one falls faster. Now tie them together with a string. Drop them. What happens? If the heavy one falls faster, the string pulls taut. The light stone drags behind, slowing the heavy one down. So the system falls slower than the heavy stone alone. But wait, the system of both stones together is heavier than the heavy stone by itself. So it should fall faster than the heavy stone alone. Contradiction. The assumption must be false. He says if you unite 2 bodies, the faster one will be retarded by the slower, and the slower hastened by the faster. But if this is true, and a large stone moves with speed 8, while a smaller moves with speed 4, then when tied together, the system moves with speed less than 8. But the 2 stones together make a stone larger than the one moving at speed 8, so it should move faster. Aristotle is caught in his own logic. Notice what Galileo does not do. He does not just say Aristotle is wrong by dropping objects and measuring. That comes later. First, he shows Aristotle cannot be right by pure reason. The thought experiment is a trap. If Aristotle is correct, you get contradictions. So Aristotle must be incorrect. This is the first stroke of genius, destroying the old framework before building the new one. Because proving Aristotle wrong is not the same as proving what is right. Between Aristotle saying heavy falls faster and Galileo saying all fall the same, there is a universe of possibility. So Galileo needs experiments, not just thought experiments, real ones. They hit the ground together, professors and students watch. Aristotle is defeated in public. It is a perfect story, dramatic, visual, memorable. There is one problem. Galileo never mentions it in any of his writings, not once. The story comes from Vincenzo Viviani, Galileo's student and assistant, who writes a biography in 1654, 12 years after Galileo dies. Viviani claims Galileo performed repeated experiments from the height of the Leaning Tower in the presence of other professors and all the students, but we have no contemporary accounts, no letters, no university records, nothing from Galileo himself. He says Galileo worked through thought experiments in mathematics, not public demonstrations, but Stillman Drake and Galileo at Work, published 1978, pushes back. He says Galileo's early work in De Motu mentions drops from a high tower. Drake argues a public demonstration fits Galileo's combative personality and his documented anti-Aristotelian stance at Pisa. The debate is not settled. We do not know if the Leaning Tower experiment happened. We know Galileo believed it would work. We know by 1641, his successor at Pisa, Vincenzo Ranieri, actually did the experiment. Ranieri dropped lead and wooden balls from the tower. The lead ball hit first, air resistance. Galileo predicted this. A cannonball weighing 100 or 200 pounds and a musket ball weighing half a pound, both dropped from a height of 200 cubits, will not differ by more than a span when they hit the ground. The cannonball reaches the ground only 2 finger breadths ahead of the musket ball. Aristotle claimed the difference would be 99 cubits. Galileo says you would not hide behind those 2 fingers the 99 cubits of Aristotle. The error is massive. What if falling and rolling down a ramp are the same motion, just diluted? Gravity pulls straight down. On a ramp, only part of that pull moves the object down the slope. The steeper the ramp, the faster it rolls. The shallower, the slower. But the character of the motion, the acceleration, should be the same, just stretched out in time. A piece of wooden molding or scantling, about 12 cubits long, that is roughly 7 meters, half a cubit wide, about 30 centimeters, 3 finger breadths thick, about 5 centimeters. On its edge, he cuts a channel a little more than 1 finger in breadth. He makes the groove very straight, smooth, and polished. He lines it with parchment, also as smooth and polished as possible. Why parchment? To reduce friction. He rolls along at a hard, smooth, and very round bronze ball. So Galileo invents a water clock specifically for this experiment. After each descent, he weighs the water on a very accurate balance. The differences and ratios of these weights give him the differences and ratios of the times. This is brilliant. Weight does not change. Time is hard to measure directly. But if water flows at a constant rate, the weight of the water is a perfect proxy for time. He measures the time with such accuracy that the deviation between 2 observations never exceeds 1/10 of a pulse beat. Then he does something systematic. He rolls the ball down only 1/4 the length of the channel. He measures the time. He finds it is precisely 1/2 the time for the full length. Think about that. 1/4 the distance takes 1/2 the time. Not 1/4 the time, half. He tries other distances. 1/2 the length, 2/3, 3/4, any fraction. He repeats these experiments a full 100 times, always the same result. The spaces traversed are to each other as the squares of the times. For time 4, distance 16, the pattern is 1, 3, 5, 7. The distances covered in each successive equal time interval are the odd numbers. 1 unit in the first second, 3 more units in the second second, 5 more in the third. This beautiful numerical progression, as Galileo calls it, proves the ball is accelerating uniformly, constantly speeding up, not reaching a steady speed like Aristotle thought. Galileo observes that the times of descent for various inclinations of the plane bear to one another precisely the ratio he had predicted and demonstrated mathematically. He notes this in 2 new sciences. The steeper the ramp, the faster the acceleration. But the relationship holds. This is experimental physics, controlled, repeatable, measured. This is the method that will build the modern world. Galileo argues that what happens on the ramp is exactly what happens in free fall, just faster. A ball falling straight down is the limiting case of a ball rolling down a ramp as the ramp gets steeper and steeper until it is vertical. The acceleration is the same in character, just different in magnitude. He tested this with a pendulum and a nail, as he mentions on page 171 of 2 New Sciences. He shows that the speed gained rolling down a ramp of a given height does not depend on the slope. Only the height matters. This means the motion is fundamentally about gravity and height, not about the path taken. The acceleration is uniform. This is why Galileo's law works. It is not about the object. It is about the space it moves through. He says we infer large and small bodies move with the same speed provided they are of the same specific gravity. Then he admits. Simplicio is not entirely wrong. He says a birdshot and a cannonball will not reach the ground at exactly the same time. The cannonball will arrive slightly ahead. Why? Air resistance affects the lighter object more. For extremely light objects like feathers, air resistance becomes dominant. For heavy compact objects, air resistance makes only a small difference. This is why Aristotle was not completely insane. In normal experience, watching objects fall through air, heavier objects do often fall faster. Not because of their weight directly, but because air resistance affects them less. Aristotle confused correlation with causation. Heavier objects usually fall faster, not because weight causes faster fall, but because weight correlates with density and size, which affect air resistance. Objects accelerate uniformly under gravity regardless of their mass. This is the foundation. That is observation. Galileo says observation is corrupted by complications. Air resistance, friction, shape. If you want to understand the law underneath, you need to remove the complications. You need to idealize a ball rolling down a perfectly smooth ramp, a medium with no resistance. This is not the real world. The real world is messy. But the messy world is the clean law plus complications. Understand the clean law first. Then add back the complications. Something Galileo himself does not fully understand. Something that will take 300 more years to unpack. Two masses tied together fall at the same rate as each mass alone. Why would this be true? Newton will later formalize this. He will say gravitational force is proportional to mass. F equals g times m1 times m2 divided by r squared. The force of gravity on an object is proportional to its mass, but Newton also says force equals mass times acceleration. F equals ma. So if gravitational force is proportional to mass, and force equals mass times acceleration, then the mass cancels out. Acceleration equals g times m divided by r squared. The acceleration does not depend on the mass of the falling object, only on the mass of the Earth and the distance to its center. It measures resistance to acceleration. The mass in the gravitational force law is gravitational mass. It measures how strongly an object responds to gravity. These are conceptually different things. One is about inertia, one is about gravity. Why are they equal? Why are they even proportional? Newton notices this. He calls it a coincidence, a very precise coincidence. He measures it with pendulums. He finds that gravitational mass and inertial mass are the same to within experimental error, but he does not know why. It is something else entirely. Not similar, identical. There's no experiment the person can do inside the elevator to distinguish between them. Acceleration and gravity are equivalent. This is the equivalence principle. This sounds insane, but it explains everything. It explains why all objects fall at the same rate, because they are all following the same curved paths through space-time. The path does not depend on the mass of the object. It depends only on the curvature of space-time itself. Einstein calls this Galileo's law of free fall. He says Newton recognized this law implied the equality of inertial and gravitational mass. But for Newton, the connection was accidental. For Einstein, it is the key to understanding gravity itself. Galileo's falling balls, rolling down ramps in Padua in 1603, point the way to the curvature of space-time. He publishes dialogue concerning the two chief world systems. This is about Copernicus, the sun at the center, the earth moving. The church is not happy. Galileo is tried by the Inquisition, forced to recant, sentenced to house arrest for life. He spends his final years under guard in Arcetri, near Florence. Published in Leiden in 1638 by Lodewijk Elsevier. Why Leiden? Because after the dialogue, the Roman Inquisition bans publication of any work by Galileo, including anything he might write in the future. So Elsevier publishes it in the Netherlands, where the Inquisition has no power. The book reaches Rome in January 1639. 50 copies. They sell out immediately. 30 years of work on physics. It covers the strength of materials and the science of motion. The motion section is everything: falling bodies, projectiles, acceleration, the inclined plane experiments, the water clock, the law that distance is proportional to time squared, the parabolic path of projectiles. This is the foundation of classical mechanics. Newton will read this. He will build calculus on top of it. He will derive universal gravitation. But the foundation is Galileo's. Salviati proposes his newest models. The three characters are Galileo at different stages of his life, arguing with himself. This is how science works. You challenge your own ideas. You test them. You refine them. You move forward. He derives this mathematically using the theory of proportions from Euclid. He then presents the inclined plane experiments as empirical proof. He gives the exact setup, the exact method, the exact results. This is modern experimental science: hypothesis, derivation, experiment, verification. It falls downward with uniform acceleration. The two motions combine. The path is a parabola. Galileo proves this. He shows that if you know the initial speed and the angle of launch, you can calculate exactly where the projectile will land. This is ballistics. This is engineering. This is power. In the absence of air resistance. This fact seems trivial now. We teach it to children. But it was not obvious. It took a specific kind of mind to see it. A mind that could separate observation from law, that could build controlled experiments, that could measure precisely, that could think mathematically, that could challenge authority, that could be wrong and correct itself. Under house arrest in Arcetri. He is 77, blind in his final years. Attended by Vincenzo Viviani, the student who will later write the biography and claim the Leaning Tower experiment, Galileo is buried in the Church of Santa Croce in Florence. Later, in 1737, they build a monument, move his body to a more prominent tomb, opposite Michelangelo. In 1649, 7 years after Galileo dies, Christian Huygens derives the formula for centripetal acceleration using Galileo's work. In 1687, Isaac Newton publishes Philosophiae Naturalis Principia Mathematica. The Principia, universal gravitation, the three laws of motion, the mathematical principles of natural philosophy. Newton says, if I have seen further, it is by standing on the shoulders of giants. Galileo is one of those giants. Undeniable. If gravitational and inertial mass were not exactly equal, the moon would fall differently. It does not, to within 1 part in 10 billion. The equivalence principle, the foundation of general relativity, is confirmed again and again. Every test passes. The theory stands. Distance proportional to time squared. From that, everything else followed. He had to design an experiment that could actually test the question. Falling is too fast. Slow it down with a ramp, but make sure the ramp is smooth enough that friction does not dominate. Parchment, bronze, polished. He had to measure precisely. The water clock, weighing the water, repeating 100 times. 1/10 of a pulse beat accuracy. He had to see the pattern. The distances covered in each interval are 1, 3, 5, 7, the odd numbers. This means the total distance is 1, 4, 9, 16. The squares. Distance proportional to time squared. Acceleration. His early work, De Motu, still has Aristotelian assumptions. He thinks specific gravity matters for falling speed. He thinks only objects of the same material fall at the same rate. It takes him decades to get to the full truth. All objects fall at the same rate, regardless of mass or composition. In vacuum. This is the scientific process. You start with an idea, you test it, you find it is wrong, you refine it, you test again. You get closer to the truth. You never quite arrive. But you build up a body of knowledge that works, that predicts, that allows you to do things. This is the Enlightenment. This is modernity. This is the idea that we can understand the world by observing it carefully, thinking about it clearly, and testing our ideas rigorously. Force equals mass times acceleration. Gravitational force equals gravitational constant times mass of object times mass of Earth divided by distance squared. Therefore, acceleration equals gravitational constant times mass of Earth divided by distance squared. Mass of object cancels. Acceleration is the same for all objects. But Newton admits this is strange. Why does mass appear in both places? Inertial mass and gravitational mass. Why are they equal? The Earth moves through that curved space-time. The path is determined by the curvature, not by the Earth's mass. We still do not know if this is exactly true at all scales. General relativity predicts it. Every experiment confirms it. But at the quantum level, things get weird. Quantum mechanics and general relativity do not fit together. We do not have a theory of quantum gravity. We do not know if the equivalence principle holds for quantum particles in superposition states. We do not know if space-time is continuous or discrete at the Planck scale. We are still testing, still probing, still looking for the deeper truth. In 2009, physicists recreate Galileo's falling bodies experiment at Pisa, not from the tower, in a lab. Using modern equipment, they confirm his results. The experiment works exactly as he described. This is 400 years later. The science holds. Measurements from the inclined plane experiments. This is the raw data, the actual measurements. They match what Galileo published in 2 New Sciences. He really did the experiments, 100 times. Weighing water, measuring distances, finding the law. Alexandre Koyré argued this. He said the experiments were thought experiments, too precise to be real with the technology of 1603. But then they replicated the experiments, with the exact setup Galileo described. Wooden ramp, water clock, bronze ball, and it works. The precision Galileo claimed is achievable. He really could measure to 1/10 of a pulse beat. The water clock really is that accurate if you weigh the water, instead of trying to mark time intervals. The realization that you can separate the pure law from complicating factors like air resistance, the insight that acceleration is uniform, not that objects reach a steady speed, the method of controlled experiment, precise measurement, mathematical analysis. This is the package. This is what Galileo gives us. He got the professorship at Pisa partly because of family connections. He was combative. He made enemies. He almost lost his position. He moved to Padua in 1592. Better pay, more freedom. It is in Padua that he does the inclined plane experiments. If he had stayed at Pisa, maybe he never does them. Maybe the Inquisition shuts him down earlier. Maybe the work never happens. It depends on specific people making specific choices at specific moments. Galileo chose to challenge Aristotle. He chose to build the ramp. He chose to repeat the experiment 100 times. He chose to publish even when it was dangerous. These choices matter. Pope John Paul II says the Galileo case was a tragic mutual incomprehension. The Church thought faith and science were opposed. They were not. Galileo was right. The Earth moves. The objects fall at the same rate. The method works. It took Galileo. It took courage. It took genius. This is learning how to think, how to separate truth from appearance, how to build knowledge that lasts. The atoms interfere with themselves. The interference pattern reveals their acceleration. Rubidium and potassium fall at the same rate, to within 1 part in a trillion, 417 years after Galileo rolled a bronze ball down a parchment-lined groove. The law holds. The equivalence principle stands. Galileo was right.